NEC 450.13b states that electrical equipment, such as transformers, installed in a transformer vault or transformer room, must be located so that the front of the equipment is accessible for inspection and maintenance. The code also states that no other equipment or materials may be placed in the transformer vault or transformer room that would obstruct access to the equipment. NEC 720.3a says conductors and equipment shall be installed in accordance with the provisions of Article 300. Article 300 requires that conductors and equipment be securely supported and protected against physical damage. NEC 300.3b states conductors shall not be installed in the same compartment, for example, a transformer compartment, with equipment that will produce excessive heat. Let's analyze a situation where 52 circuit wires installed in the rear lower section of a transformer compartment to feed underflow conduits are in violation of NEC 450.13b because they obstruct access to the transformers. Also, 480-volt cables running through the transformer compartment to feed a lighting panel are in violation of NEC 300.3b because they are installed in the same compartment with transformers, which could produce excessive heat. So, firstly, relocate the 52 circuit wires to an accessible area outside of the transformer compartment. Secondly, reroute the 480-volt cables outside of the transformer compartment or install them in a separate compartment. Ensure all wiring and equipment installations comply with the National Electrical Code (NEC) to guarantee safety and proper functionality. Remember that access to electrical equipment like transformers must remain unobstructed for inspection and maintenance. The presence of other wiring or materials that hinder access violates NEC 450.13b. All conductors and equipment should be securely supported and protected from physical damage, as per NEC 720.3a on referencing Article 300. Avoid installing conductors in compartments with heat-generating equipment such as transformers to prevent overheating and potential hazards, as mandated by NEC 300.3b. In the situation described, running 52 circuit wires through the transformer compartment, especially if they impede access, directly violates NEC 450.13b. Similarly, routing 480-volt cables through the transformer compartment places them in close proximity to heat-producing transformers, violating NEC 300.3b. In such cases, relocate the 52 circuit wires to a more suitable location outside the transformer compartment to restore accessibility. Reroute the 480-volt cables away from the transformer compartment or, if necessary, install them within a separate, adequately ventilated compartment to mitigate heat exposure. Proper adherence to these codes ensures a safe and compliant electrical installation, minimizing risks associated with obstructed access and excessive heat. Furthermore, consider the physical protection of conductors. The NEC mandates that conductors must be protected from physical damage. Running them through a transformer compartment where tools or equipment could be inadvertently dropped on them creates a risk of damage. This can lead to short circuits, ground faults, and potentially arc flash events. Securely supporting the conductors is also essential. Loose or unsupported conductors can sag, creating strain on connections and increasing the risk of insulation damage. Proper supports, such as cable trays or conduit clamps, should be used to maintain the integrity of the wiring system. When dealing with transformers, it's important to understand their operating characteristics. Transformers generate heat as a byproduct of their operation. The amount of heat generated depends on the transformer's size, load, and efficiency. Enclosing conductors in the same compartment as a transformer can exacerbate the heat buildup, potentially leading to conductor insulation breakdown. This can result in short circuits and other electrical faults. The NEC provides guidelines for the proper ventilation of transformer compartments to prevent overheating. These guidelines should be followed to ensure that the transformer operates within its safe temperature limits. In addition to the specific code sections mentioned, other relevant NEC articles may apply to this situation. For example, Article 310 covers conductor ampacity, which is the maximum current a conductor can carry continuously without exceeding its temperature rating. The ampacity of conductors must be derated when they are installed in high-temperature environments, such as transformer compartments. Article 408 covers panel boards, which are used to distribute electrical power to branch circuits. Panel boards must be properly sized and protected to prevent overloads and short circuits. The NEC also contains requirements for the grounding of electrical systems. Proper grounding is essential for preventing electrical shock hazards and ensuring the safe operation of electrical equipment. When performing electrical work, it's important to consult the latest edition of the NEC and follow all applicable codes and standards. Failure to do so can result in unsafe installations, equipment damage, and potential legal liability. Proper planning and execution are crucial for ensuring a safe and compliant electrical installation. This includes selecting the appropriate wiring methods, providing adequate physical protection, and ensuring proper ventilation. It also involves coordinating with other trades, such as mechanical and plumbing contractors, to avoid conflicts and ensure that all systems are installed correctly. Electrical inspections are an important part of the construction process. Inspectors verify that electrical installations comply with the NEC and other applicable codes. They also identify potential hazards and ensure that the electrical system is safe for use. It's important to cooperate with electrical inspectors and address any issues they identify promptly. Ignoring code violations can have serious consequences, including fines, project delays, and potential safety hazards. A transformer is a static electrical device that transfers energy by inductive coupling between its winding circuits. Electrical transformers are most commonly used to increase or decrease voltage levels between circuits. Transformers are essential components of any electrical grid. A transformer works on the principle of electromagnetic induction. Transformers require alternating current to operate. A transformer can also be used to provide electrical isolation between two circuits. A transformer will consist of two or more coil windings electrically isolated but magnetically linked. A transformer's core is made of laminated silicon steel. The core provides a low reluctance path for the magnetic flux. One winding is connected to an alternating current source and is called the primary winding. The other winding is connected to the load and is called the secondary winding. When alternating current flows through the primary winding, it creates a fluctuating magnetic field in the core. This fluctuating magnetic field induces a voltage in the secondary winding. The voltage in the secondary winding is proportional to the turns ratio of the transformer. The turns ratio is the ratio of the number of turns in the secondary winding to the number of turns in the primary winding. The amount of voltage induced in the secondary winding is directly proportional to the number of turns of the secondary winding, assuming the magnetic flux in the core is the same. If a transformer has more turns in the secondary winding than in the primary winding, it is called a step-up transformer. A step-up transformer increases the voltage from the primary winding to the secondary winding. If a transformer has fewer turns in the secondary winding than in the primary winding, it is called a step-down transformer. A step-down transformer decreases the voltage from the primary winding to the secondary winding. The power in the primary winding is equal to the power in the secondary winding, assuming no losses in the transformer. Therefore, if the voltage is increased, the current is decreased, and vice versa. Transformers are used in a wide variety of applications, including power transmission, power distribution, and electronic circuits. In power transmission, transformers are used to step up the voltage of electricity generated at power plants for transmission over long distances. This reduces the current and minimizes losses in the transmission lines. At substations, transformers are used to step down the voltage for distribution to homes and businesses. In electronic circuits, transformers are used to isolate circuits, match impedance, and step up or step down voltages. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is not law, but it is often adopted by state and local jurisdictions as their electrical code. The NEC is updated every 3 years to reflect changes in technology and best practices. The NEC covers a wide range of topics including wiring methods, overcurrent protection, grounding, and equipment installation. It is a comprehensive document that provides detailed requirements for virtually every aspect of electrical work. The electrical codes and standards are important for ensuring the safety of people and property. They provide a framework for the safe installation and operation of electrical systems. By following these codes and standards, electrical workers can help prevent electrical shocks, fires, and other hazards. A panel board is a component of an electrical distribution system that divides an electrical power feed into subsidiary circuits, while providing a protective circuit breaker or fuse for each circuit in a common enclosure. A panel board is also known as a load center or breaker panel. Panel boards are typically installed in homes and businesses to distribute electricity to various branch circuits. A branch circuit is a circuit that extends from the panel board to an outlet, lighting fixture, or other electrical device. Panel boards are rated for a maximum voltage and current. The voltage rating indicates the maximum voltage that the panel board can safely handle. The current rating indicates the maximum current that the panel board can safely distribute. Panel boards must be installed in accordance with the NEC. The NEC specifies the requirements for the location, mounting, and wiring of panel boards. The NEC also specifies the requirements for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect the panel board and branch circuits from overloads and short circuits. When selecting a panel board, it is important to consider the following factors. First, consider the voltage and current requirements of the electrical system. Second, consider the number of branch circuits that will be needed. Third, consider the location where the panel board will be installed. Fourth, consider the available space. Panel boards are available in a variety of sizes and configurations. Choose a panel board that meets the needs of the electrical system and the available space. An underfloor raceway is a duct, usually rectangular, that is designed and intended for installation underfloor for housing power, data, and telecommunications cabling. Underfloor raceways provide a flexible and accessible way to distribute wiring in commercial and industrial buildings. Underfloor raceways are typically made of steel or aluminum and are available in a variety of sizes and configurations. They can be installed in concrete slabs, raised floors, or other types of flooring systems. Underfloor raceways provide a number of advantages over traditional wiring methods. Firstly, they allow for easy access to wiring for maintenance and repairs. Secondly, they provide a flexible way to add or change wiring as needed. Thirdly, they protect wiring from physical damage. Fourthly, it can improve the appearance of a space by concealing wiring. Underfloor raceways must be installed in accordance with the NEC. The NEC specifies the requirements for the location, mounting, and wiring of underfloor raceways. The NEC also specifies the requirements for grounding. Proper grounding is essential for preventing electrical shock hazards and ensuring the safe operation of electrical equipment. When installing underfloor raceways, it is important to consider the following factors. Firstly, consider the type of flooring system. Secondly, consider the size and configuration of the raceway. Thirdly, consider the location of the raceway. Fourthly, consider the grounding requirements. Underfloor raceways are a versatile wiring solution for commercial and industrial buildings. By following the NEC and best practices, electrical contractors can ensure that underfloor raceways are installed safely and effectively.